Starting off a new chapter, chemical bonding, we're going to be talking about the Lewis model. As the title of the chapter suggests, chemical bonding 1. There's also a chemical bonding 2. That's chapter 11. So bonding models have been around for a while. An important notable time that bonding models have been used was 1989. The structure of HIV protease was determined. That's a protein that's synthesized by HIV, and because of those developments, because of figuring out the structure of HIV protease, researchers were able to design a couple of molecules that would disable the HIV protease by binding to the active site. This is used a lot more now since we've got better computational models. So you can figure out the target that you're trying to hit with a drug and then have a computer come up with 100,000 or more different chemicals that might work for that, have it throw all those chemicals at it in a simulation, see which one of those work best, narrow that list down, refine it a couple more times, and then actually have people make and test those drugs. So that it's really good that we've got all these great bonding models. Most of those bonding models are very computationally intense, and so you have to do them in a computer with all these parameters and frameworks and other stuff that's going on. We're not going to be doing any of that. We're going to be doing the very most basic, simple bonding models. So bonding theories can do some cool things for us. They can explain how atoms bond together. So how many single bonds, double bonds, triple bonds there are, when they form molecules, and the arrangement of the atoms in those molecules. Can explain why some molecules and some forms are stable and others are not. We can also use it to predict the shape of molecules, and the shape is important because it determines some of our chemical and physical properties. We're going to be using relatively simple models, and so they are not quite as powerful as the very computationally intense models, but that's okay. So the model that we are going to be using is the Lewis model. In the Lewis model, valence electrons are represented as dots. Remember that valence electrons are in the highest n level, or principal quantum number level, highest shell or row number when we're doing electron configurations. So our Lewis electron dot structures depict molecules. We can predict shapes of molecules with some extra tools, and we can tell if a molecule is likely to be stable. We can also have different types of chemical bonds that show up depending on what kind of molecules we have or what type of chemical compound we have. The reason that chemical bonds form is because they lower the potential energy between the charged particles that compose atoms. Bonds lower the energy. They are stable. Bonds that form are stable. It lowers the energy of the atoms that go into it. In order to break the bond, you'd have to put in energy. I believe we've talked about this briefly. When atoms approach each other, there's some interactions that go on. The electrons are going to repel each other. The nuclei are going to repel each other. Remember that electrons are negatively charged. Our nuclei have all of our positive charge in them. But the electrons and the nuclei are attracted to each other. Because they are negatively and positively charged respectively. A bond can form if those interactions result in a net reduction in energy. So if the attractive force is greater than the repulsive forces, then we can get a bond to form. One of our types of bonds is ionic bonds. Metals, found on the left and lower side of the periodic table, have low ionization energies. It's easy to remove an electron. Nonmetals in the upper right part of the periodic table have negative electron affinities, like to / easy to accept an electron. These are some of the trends that we talked about last class. So metals like to give up electrons, or it's relatively easy to remove electrons. Nonmetals, it's relatively easy to accept an electron. So metals can give electrons to nonmetals. So we get a transfer of an electron from a metal to a nonmetal, and that forms an ionic bond. We also have covalent bonds. The co, like in cooperative, meaning shared or working together. Covalent bonds are shared valence electron bonds. So rather than transferring an electron, we are sharing electrons. This is when nonmetals interact typically. They're going to share some of their electrons from their outer valence shells. The lowest energy place for those electrons to live is between the two nuclei. You could sort of think of bonds as like putting a rubber band around the two atoms. If you pull the rubber band up and then you let go, it's going to drop back down to between the 2 points that you have it between. That's where we're most likely to find our electrons. That's the most stable position. We also have metallic bonding that can occur between metal atoms. Metals lose electrons easily. The simplest model for metallic bonding is the electron C model. And essentially what we've got here, we've got a bunch of positively charged metal nuclei, and the electrons just kind of flow freely whatever way they want to. So we've got a baseline of lots of nuclei, and the electrons just kind of flow freely through and between the nuclei. All right, with our Lewis theory, our valence electrons are the star of the show. They're the most important for our chemical bonding. These are in the outermost principal energy level, the highest N level. These are the outermost shell of electrons. Since they're the outermost ones, these are the ones that are first to be able to interact with other things, other atoms. I'm going to switch this to nitrogen instead of oxygen. For a Lewis symbol, this is our first building block for the Lewis theory. Valence electrons are shown as dots around the element symbol. So for nitrogen, our symbol is N. How many valence electrons does nitrogen have? Nitrogen is in group 15, or 5A, so it has 5 valence electrons. If we did an electron configuration for nitrogen, we would have 1s2, 2s2, 2p3. So our valence electrons are going to be these outermost electrons, the one in our n equals 2 level. So we've got 5 valence electrons. That's one way we can get it. We can also get it from the A designation group number or column number. So nitrogen and everything below it generally will have 5. Oxygen and everything below it will generally have 6. Fluorine and everything below it will generally have 7. So we have 5 valence electrons. We can draw those in as dots. We're going to draw them in singly first, in north, east, southwest directions, and then we can double them up. The location of the dots is not critically important. So you could draw the double dots instead of on the left. You could draw them on the top, you could draw them on the right, you can draw them on the bottom. The most important thing is that we've got electrons on all 4 sides, and one of those sides has 2 dots to give us 5 dots. So dots are placed with a maximum of 2 per side, using nitrogen again as our example. Those sides are up, right, left, down. Atoms that get or have 8 valence electrons are said to have an octet. The oct, like in octopus, stands for 8. An octet is particularly stable. There are some exceptions to the octet rule. Helium is an exception. It gets a duet. A duet, like 2 people singing together. So a duet is 2 electrons. Small atoms are happy with a duet. Otherwise, generally, we are looking for octets. So our octet rule is that our atoms transfer or share electrons to achieve an octet of valence electrons. This is noble gas configuration, or something similar to being a noble gas configuration. We know that our noble gases are especially stable. That's why we can use helium in party balloons, and our party balloons don't explode if you accidentally pop one next to a birthday cake. It's also why we can use neon in those light up signs, and if the light up sign breaks, it doesn't explode. If you use hydrogen or if you use some other gases, if you broke the sign, all that energy would probably just explode, which would not be fun. Questions so far? Most of this should be review for Chem 20. Question?
Is there any other exceptions?
There's lots of exceptions. One of the other exceptions, I might talk about it later. I don't remember if it's in these slides. Boron and aluminum like to have 6 valence electrons. This is once we're starting to put them into compounds. When they're just by themselves, they'll have their normal 3. Hydrogen also happy with a duet. And what I mean by happy is that they're stable. They've minimized their energy. They're going to sit there until they're given outside energy that makes them unstable, raises their energy level. So some Lewis structures for potassium and chlorine. For potassium, our highest energy level is N equals 4. That's our valence shell, our valence level. And we've got 1 valence electron. So for potassium, we just give it 1 dot. For chlorine, how many valence electrons does chlorine have? 7. So we're going to give it 7 dots. We're going to start with them singly first, then pair them up. So it should look something like that. Again, it doesn't matter which side has the single dot. All that matters is that one side has a single dot. And when these two interact, potassium is a metal, chlorine is a nonmetal. Metals like to give electrons to nonmetals. And so we would transfer the one valence electron from potassium to chlorine. And that would turn into K+, and then in brackets, the chloride. And then we put the charge in the upper right corner. We only have to do this for anions because they've got dots around them. Potassium here, because it's a cation, doesn't have any dots, so we don't need to give it brackets. The brackets are saying that these electrons belong only to chlorine. They're not sharing between potassium and chlorine. So those brackets are showing that the electrons are only on chlorine. And for our cations, when we go from potassium to K+, the potassium ion, our 4s is now empty, and so it's got a full octet in the previous level. The n equals 3 is full, which makes potassium ion stable. Our chloride ion is also stable because it's got 8 dots around it, 2 per side on all 4 sides. So this predicts, since our potassium has a full octet and our chloride has a full octet, this predicts that our formula for this ionic compound would just be KCl, 1 potassium, 1 chloride. We can also use it to predict compounds between other metals and nonmetals, other ionic compounds. So if we have magnesium and nitrogen, for example, how many valence electrons does magnesium have? It has 2, because it's in group 2A. How many does nitrogen have? Nitrogen has 5. Who is transferring electrons to whom? Magnesium is transferring to nitrogen. So we move 2 electrons over. This is going to turn into this. Magnesium is now a 2+. We've stripped off the outer shell, the valence shell, and there's a full shell underneath that. So magnesium is happy. It's got its full octet. That's what the check mark means. Does nitrogen have an octet? No, nitrogen doesn't have an octet. How many electrons does it need? Needs 1 more electron. Where could we get that electron from? What metals do we have available to us up here? What metal do we have? Magnesium. There's probably another magnesium. If we've got 1, we've probably got 2. So we say, oh, all right, well, there might be another magnesium. That magnesium has 2 valence electrons. What if we transfer one of those electrons over? So we transfer that electron over, and now is the nitrogen happy? It sure is. We give it brackets and a 3- and a check mark. But our magnesium now has 1 valence electron, so it's not happy, so it needs to get rid of that. And it could give that to, well, another nitrogen. So, okay, there's another nitrogen around. That nitrogen can accept the 1 valence electron, which turns it into this. And now our magnesium, our second magnesium, is happy. We stripped off the valence shell. Our nitrogen is not happy. It doesn't have a full octet. Well, there's probably another magnesium lying around somewhere. And that magnesium probably also has, or will have, 2 valence electrons. We can transfer those 2 valence electrons over. And now this other nitrogen has its full octet, and our magnesium is a 2+. So it also has a full octet. Now everything that we've got, everything that we've placed down after our initial 2, these all have full octets. How many magnesiums do we have? 3. So this predicts a formula of Mg3. And how many nitrogens do we have? N2. This is, of course, not a very efficient way of coming up with ionic compound formulas. But we can do it. It works with our Lewis structures. The way that we would probably do it is we know that magnesium forms a 2+, nitrogen forms a 3-. You crisscross it, and that's a much faster way of getting to Mg3N2. But we can do it, we can show it with Lewis theory. So this is sort of what we've been doing behind the scenes when we've come up with ionic compound chemical formulas so far. This is not really why we're doing Lewis theory. But while we're here, we are going to talk about ionic compounds. The way that ionic compounds form is usually exothermic. So there's energy released. Energy emitted as our sodium and our chlorine turn into sodium chloride. Remember that this symbol here is our standard heat of F4 formation. Our standard heat of formation is the reason that we've got 1 for our subscript on the right, and we've got that 1/2 coefficient on chlorine, and that's okay. This is stuff that we covered in chapter 7, which conveniently was like last class. The reason for this can't be completely explained just by our ionization energy. So our ionization energy for sodium, positive 496 kilojoules per mole. You have to put in 496 kilojoules per mole. The electron affinity for chlorine is minus 349 kilojoules per mole. That means it will release energy as it absorbs an electron. So the transfer of the electron absorbs plus 147 kilojoules per mole. The positive means it requires energy to happen. It requires energy input to occur, and generally those things don't just happen spontaneously. So there's got to be something else going on, since our heat of formation, standard heat of formation, is a negative number. There's some other energy exchange, there's some other forces at play here, and lattice energy is that other force. Lattice energy is referring to a crystalline lattice, a framework or repeating pattern of alternating cations, positively charged, and anions, negatively charged ions. Because we've got positive and negative charges, those are attracted to each other, and so that's going to cause some stabilization. The potential energy is lowered when the opposite charges come together. Essentially, the magnet force holds them together. So the formation of the ionic compounds isn't exothermic because the metal wants to lose an electron and the non-metal wants to gain an electron. It's because the positive and negative charges that form want to stick together. The positive, the negative charges form, and then they clump together. and there's a large amount of heat that gets released when that happens. There are a couple of factors with lattice energy, and we've also got this fun diagram from our book. So as gaseous ions coalesce, the sodium and the chlorine, the negative positive charges come together, heat's emitted, and we've got this hot chunk of salt. We can do a Born-Haber cycle. This is sort of like Hess's law stuff. It's a hypothetical series of steps that represents forming the ionic compound from its constituent elements. So we can use some Hess's law stuff. We have to choose steps for which the standard heat of formation is known, and the overall change in enthalpy must also be known. The Born-Haber cycle is used to calculate lattice energy. So it uses delta H with the little plimsoll and the F. And overall change in enthalpy to calculate lattice energy. What's the energy of the positive and the negative charges being next to each other, being in their ionic compound formation? Here's a diagram of a Born-Haber cycle. So on the y-axis, we've got enthalpy, and we're showing our overall step on the left. This is our heat of formation of sodium chloride from the constituent elements. We also have the formation of the gaseous sodium, formation of the chlorine atoms from chlorine molecules, ionization of the gaseous sodium, and then you add the electron to the gaseous chlorine, and finally you form the crystalline solid from the gaseous ions. There's a whole lot of steps going on. We're not, I don't think, really going to do much with the Born-Haber cycle. You should know what a Born-Haber cycle is. And we're going to talk about a couple of new trends. So 2 trends in lattice energy. One of the trends has to do with ion size. How big are the ions? If we look at metal chlorides, so we're taking from our group 1, our alkali metals, we've got a series lithium, sodium, potassium, rubidium. Sorry, potassium, cesium, no rubidium here. Moving down group 1, and then our lattice energy that's associated with those metal chlorides. Lithium chloride has the largest value for lattice energy in terms of furthest away from 0, the most negative number. So that's the most stabilization. And as we move down, we move towards the least stable. So why does lattice energy for the alkali metal chlorides decrease as we move down the column? Our ions are getting bigger. Ions get bigger down a column. And we've looked at Coulomb's law very briefly. It was something like this, Q1, Q2 over R, where Q is charge and R is distance between the charges. There were some other things in there that were basically constants. So as the radius decreases, the energy increases. The closer the ions get, the larger the energy. Because you've got two charged particles, the closer they get together, it's like bringing two magnets closer together. The closer they get, the more strongly they're going to interact. And since we've got a positive and a negative charge, they're going to be attracted to each other. That's stabilizing, so the energy is decreasing. So that's one of our trends. Ions get bigger down a column. If the ions are bigger, they're further apart. They interact less strongly, so we get a smaller number. If we look at sodium fluoride and calcium oxide, their radius is about the same, 231 picometers between the sodium and the fluoride nuclei, 239 between the calcium and the oxide, but the lattice energy is not similar. For sodium fluoride, it's around negative 900, and it's almost 4 times as much for calcium oxide. So there's something else going on. That something else is ion charge, and this is where the Q1, Q2 come in. So ionic size doesn't explain this difference because they're about the same in terms of their internuclear distance. Lattice energy also depends on the magnitude of the charges. Higher charges means larger lattice energy. And this is a bigger effect. This is a much bigger effect because we've got Q1 times Q2. So if we have +1, -1, let's say that that's negative 500 kilojoules per mole. If we bring them a little bit closer together, that number is going to go more negative. But if we change it to +2, -1, it would be like negative 1,000 kilojoules per mole. So if we double one of the charges, we double the energy. Approximately, the radius will probably change a little bit. If we double both of the charges, 2 times 2, it's now 4 times the energy. That's why we're seeing about a 4 times difference in our lattice energy. One times 1 is 1, 2 times 2 is 4, which is why it's about 4 times bigger. So ion charge is a much bigger factor for our lattice energy compared to our ion size. Like with our lithium chloride, that's our closest distance. We could get hydrogen chloride, that'd be closer. But 241 to 348, it's like a 50% increase almost. And our lattice energy doesn't really change that much. It's not doubling or tripling or quadrupling for the charge. Questions about our lattice energy? So 2 new trends. How does radius or atomic size, ionic size affect lattice energy? How does ion charge affect lattice energy? Summary slide. This is all because energy is proportional to Q1, Q2 over R. I would expect that you'll probably get Coulomb's law for the relevant exam that covers lattice energies. So you could figure it out, you could work it out, but I would recommend a little bit of flashcard time probably thinking about lattice energies. What's the trends? Maybe do some extra problems from the book. some live, in-person predictions for lattice energy. Please arrange the following in order of increasing magnitude of lattice energy. We've got lithium bromide, potassium iodide, calcium oxide. So we're going from lowest to highest lattice energy. What are the two factors that affect lattice energy? Charge and radius. And radius is basically ionic size. So we should think about what's the charge of everything that's in our chemical compounds. For lithium bromide, what are the charges? Positive and negative. How about for Ki? Also positive and negative. What about CaO? 2 plus, 2 minus. So one of the obvious differences, hopefully an obvious difference, calcium oxide has 2 plus, 2 minus. The other ones have plus, minus, plus, minus. So these two are the same. There's got to be a different way to distinguish those. So we've been looking at charge. Calcium oxide's obviously got different charge. So we need to think about, for the other one, since the charge is the same, what about the radius? What's the ionic size going to look like? So let's find lithium bromide. Lithium is in row 2. Bromine is in row 4. And then for Ki, potassium is in row 4, and iodine is in row 5. So which one has bigger ions? Potassium iodide has bigger ions because both of the things that are involved are lower down. So bigger ions, that means that LiBr has smaller ions. Which effect is bigger, charge or radius? The charge is bigger because our energy is proportional to charge 1 times charge 2 divided by radius. If we're going from a 1 to a 2, that's going to double our energy. If we're going from a negative 1 to a 2 minus, that's also going to double our energy, so 4 times the energy. So calcium oxide, we would expect to have the highest magnitude. Charge is generally a bigger effect. So calcium oxide is going to be our highest energy. And then we have to make a distinction based on ion size. Are smaller ions or bigger ions going to have a bigger lattice energy? Smaller ions are closer together, more energy. Smaller radius, bigger energy. Smaller ions get closer. Smaller radius means bigger energy, larger number for energy. So LiBr be the next highest, and then the lowest energy would be Ki. It's got bigger ions, they're a +1, they're a -1. Bigger ions, they're further apart. It's like pulling two magnets slightly apart. They're not going to pull on each other quite as strongly. Questions or confusions? Okay. Ionic bonding models, we have high melting points because of the non-directional bonds. Positive charges are surrounded by negative charges on every side. Negative charges surrounded by positive charges on every side. So they're bonded in every which way, every which direction. The solids are non-conductive because the ions are fixed in place. They can't move around to carry charge. Solutions of ionic compounds have ions in them. Those ions can move in the solution to conduct electricity. I don't think that's incredibly important information. All right, moving on to covalent bonds, which is the real reason why we're doing Lewis structures. Lewis structures show molecular compounds as neighboring atoms. They're right next to each other. They share electrons. Molecular compounds share electrons to attain octets. Hydrogen is happy with a duet. There are also the other exception, boron, aluminum, those like 6 electrons. So let's use Lewis structure to show bonding in H2O and Cl2. We're going to learn some steps for putting together Lewis structures, so I'm just going to give us the Lewis structures for these for now so that we can look at bonding and non-bonding electrons. So these are our Lewis structures. And we've got bonding pairs and lone pairs or non-bonding electrons. The bonding pairs, in this case, are single bonds. These are electrons shared between atoms. So in our H2O, between our hydrogen and our oxygen, we've got a single bond. In each of the bonds, we have 2 electrons. And those electrons count for both atoms. I don't know where the apostrophe goes, but it's probably there. Count for both of the atoms octet/duet. So hydrogen has 2 electrons on it. That's a duet. It's happy. The other hydrogen has 2 electrons. Because of the 1 bond, it's also happy. Oxygen has 2 bonds with 2 electrons each, plus it has 2 lone pairs. The lone pairs are here in green, the green dots, 2 4 electrons. So it's got an octet of 8. So count each line or each bond as 2. So 2, 4, 6, 8. Full octet. For chlorine, we just have 1 bond between the 2 chlorines. So we've got 2 electrons from that bond. 2 electrons from the bond. Six electrons from lone pairs. The lone pairs, the sets of dots, only count for the atom that they're on. So again, each line equals 2 electrons. Each dot is 1 electron. Typically, they'll be paired up. We can also have double and triple covalent bonds, so they can have more than just one line between them. Two atoms can share more than one electron pair. For example, O2 forms a double bond, and we would also have some extra lone pairs. Since we've got 2 lines, and they're 2 electrons each, we've got 4 electrons from the double bond. So 4 electrons from the double bond. We've got 2 lone pairs. So that gives us 8 electrons, which is an octet. We can also have a triple bond, like shows up in N2. So they get a triple bond and 1 lone pair. So since we've got 3 lines and each line is 2 electrons, we've got 6 electrons. Plus 2 electrons in the lone pair. We've got 8 electrons, so we've got octets, so they're happy, in quotation marks. Do we have questions about counting up valence electrons? If they're lines, they count towards both. If they're dots, they only count for the thing that they're right next to. Every line is 2 electrons. There are other ways of showing it other than using lines, but we're just going to use lines for the class. If you go on to take OChem, you'll use lines in more obscure ways. The Lewis model also predicts stability for H2O and H3O and H3O plus and H2O2. We already looked at H2O. Our hydrogens have 1 bond. 1 bond is 2 electrons. Hydrogen likes a duet, so it's happy. The other hydrogen's in the same boat. Our oxygen has 2, 4, 6, 8 total electrons. If we were to look at H3O, H3O plus, H2O2, we would also find that they're stable or unstable. Let's do H2O2, hydrogen peroxide. Hydrogen peroxide looks like this. Would have a different shape, but something to that effect. If we're looking at our hydrogens, notice they've got 1 bond. 1 bond is 2 electrons. Hydrogen likes to have 2 electrons, a duet, so the hydrogens are happy. If we look at our oxygens, they're in the same condition. They each have 2 bonds. They each have 2 lone pairs. Two bonds, 2 lone pairs, 8 electrons, so the oxygens are also happy. Unlike ionic bonds, covalent bonds are highly directional because they're just shared between two atoms rather than being positive and negative charges all the way around. So covalent compounds, when they form as discrete individual molecules. Rather than a lattice, a repeating pattern of positive negative charges. Because of that, they have relatively weak forces between the molecules, so the molecules aren't going to stick together very well compared to that sea of positive and negative charges, which means that they're going to tend to have lower melting points. We're also oversimplifying quite a bit when we're just showing our dots for electrons. Electrons are not always shared equally. We can have polar covalent bonds that result from unequal sharing. These are less evenly shared than pure covalent bonds. So it's not perfectly sharing, but also not a transfer of electrons, like we had with ionic bonds. So HF is an example of this. Hydrogen holds the electrons or pulls on the electrons relatively weakly. Fluorine pulls on the electrons relatively strongly. So fluorine sort of hogs the electrons. This is like if you grew up with older or younger siblings and you had to share like video game consoles or toys. Usually somebody ended up having an unfair amount of time, and it was probably always the other person, or at least that's the way it felt. Why do they get to spend so much time playing the, whatever game console, and I don't? This is that for electrons and atoms. The atoms both want to play with the electrons, but somebody is going to be stronger or have more favor, so they're going to get to hold the electrons more. And the force that's behind that is electronegativity. Electronegativity is essentially how strongly an atom pulls electrons. This is sort of like specifically within chemical bonds. It's inversely related to atomic size. Fluorine gets the max value of 4.0. And then everything else is lower than that. So we've got a three-dimensional periodic table. It's sort of just skewed a little bit. And then on our y-axis, how tall each of these is showing the electronegativity. So fluorine's the tallest, and then everything sort of cascades down from fluorine. Noble gases are really unreactive, so we don't include them in electronegativity. On the yellow sheet, in the bottom right corner, if you have it out, fluorine has a 4.0 in that corner. That's the electronegativity, and you can see the electronegativity for all the other elements on the yellow sheet as well. You can also look up electronegativity values. You don't need to memorize electronegativity values, but I would recommend memorizing that 4 is the max value and that fluorine has it. So you don't need to memorize electronegativity values. En is how I shorten electronegativity. We want to arrange these elements in order of decreasing electronegativity. We've got phosphorus, sodium, nitrogen, and aluminum. Where's our highest electronegativity value on the periodic table? It's fluorine. So it is the halogens. It's all the way to the right. It's also as high up as you can go. So fluorine's the highest. Everything else sort of cascades down from fluorine. So electronegativity increases generally up and to the right. So we're essentially just looking at what's closest to fluorine. What's closest to fluorine? Nitrogen. Then what's next? Phosphorus. And then aluminum. And lastly, sodium. So we would be picking A. Nitrogen's closest to fluorine, so it's got a relatively high value. Phosphorus, being a little bit further away from fluorine, has a lower value. Aluminum, even further away, lower value. Sodium's the furthest of these, so it's got the lowest value. You had your yellow sheet out, you would also see that that's true. So nitrogen's a 3, phosphorus is 2.1, aluminum's 1.5, sodium's 0.9. So it's pretty steadily decreasing from fluorine over to sodium. The degree of bond polarity depends, at least in part, on electronegativity difference. So delta En is the electronegativity of our first element minus the electronegativity of our second element, and we'll add some absolute value bars. So we're just looking at the number. We don't care if it's negative or positive, just make it positive. And we've got these rough guidelines. For pure covalent or nonpolar, it's going to be 0 to 0.4. Polar, 0.4 to 2.0. And ionic, 2.0 and up. Again, these are arbitrary cutoffs. They're just sort of made up. In reality, it's more of a continuous spectrum of 0 electronegativity being completely covalent, and as you increase the electronegativity difference, it gets more and more polar until it gets into the ionic territory. There's another way that we can define an ionic bond. Ionic bonds show up in ionic compounds. Do we remember what's in an ionic compound? What types of things? Metal and a nonmetal. So you can also generally use that as a way of determining if something is an ionic bond. If you've got a metal and a nonmetal, it's probably going to be an ionic bond. We can also actually measure it with dipole moment, which is a way of measuring the bond polarity. Dipole moment is just a separation of positive and negative charge. We're not really going to do that. We'll talk briefly about percent ionic character. So we talked about 2 slides ago. The whole thing is on a spectrum, completely equally sharing electrons to very unequally sharing electrons. And in reality, the reason we have percent ionic character is because there's not actually a complete transfer of electrons. So 100% on our percent ionic character, our y-axis here, this would mean the electron is completely transferred. A 0 means there's no change or no transfer in electron. Our electronegativity difference is here on the x-axis. So over on the left side would be everything that's like nitrogen bonded to nitrogen. They have the same electronegativity, so there's going to be no electronegativity difference. All the way on the right side, we've got our biggest differences in electronegativity, like between potassium and fluorine. Potassium being way over on the metal side, fluorine being, of course, a 4 on our electronegativity scale, and then a whole bunch of stuff in between. Notice that none of these bonds are at the 100% mark. They're not actually completely transferring the electrons. So anything that's over 50% ionic character on this graph, we're calling ionic. I don't expect this to show up on an exam. The important idea, if it was to show up on the exam, the important idea is that we're not actually completely transferring the electrons. The whole thing is just on a spectrum. You might also notice that all of these are metal and nonmetal, just various metals and nonmetals. HF is nonmetals only. It's below 50% ionic character. That would be a molecular compound. Questions so far? Okay. We want to determine whether the bond formed between each pair of atoms is nonpolar covalent, polar covalent, or ionic. And our rough difference in electronegativity cutoffs, 0 to 0.4, 0.4 to 2, 2.0 and plus. So the numbers to remember, 0.4 and 2. What's our electronegativity difference going to be between iodine and another iodine? It's got to be 0, right? Regardless of what the value is, it has to be 0. Iodine is a 2.5. The other iodine is also going to be a 2.5. This is always going to be true if you've got the same thing, something bonded to itself. It's always going to be 0 because they've got the same electronegativity. They got the same electron pulling force. So 2.5 minus 2.5, we get a big goose egg, 0. So this is nonpolar covalent or pure covalent. Perfect sharing of electrons. With CS and Br, any guesses? Where's CS on the periodic table? Way in the bottom left. Where's Br? It's more upper right. If we look at our numbers, Br is 2.8, CS is 0.7. Difference in electronegativity, 2.8 minus 0.7. That gives us a value of 2.1. That would fall into the ionic category. We could also say that it's ionic because we've got metal and nonmetal. So if we completely forgot, I don't know what electronegativity is, I don't know what any of this stuff means. If we remember our definition for ionic compounds, metal and nonmetal, we could also make a pretty good educated guess that it's probably an ionic bond. And then, last but not least, PNO. Phosphorus has a 2.1, oxygen has a 3.5. So our difference in electronegativity, 3.5 minus 2.1, it's a difference of 1.4, which is going to be polar covalent. Questions about how we got any of those? I don't anticipate that I'll give you the table, this table, on an exam. So I would recommend memorizing the 0.4 and the 2.0 for the difference in electronegativity. You will have electronegativity values if you need them. If I give you something like iodine and iodine, I expect you to know that it's nonpolar because it's the same thing. If I give you a metal and a nonmetal, I expect you to guess that it's ionic because it's a metal and a nonmetal. And then a bonus, in the bond between phosphorus and oxygen, who is hoarding the electrons? Which side is more negative? Which one's pulling the electrons more strongly? Probably oxygen. Why oxygen? It's closer to fluorine. It's got a higher electronegativity value. And so that's going to have our negative side. So the oxygen is the partially negative side. Because it has a higher electronegativity value. And then the last little thing that I'll share with us here is there's a mnemonic device that for some reason I've remembered since like first quarter OChem. I think it was OChem. For electronegativity, the mnemonic device is Fonkel brick ship, which makes no sense. Fonkel brick ship. What does it mean? What does it mean? Fonkel brick ship is the order of electronegativity. For the first like 10 elements. I don't know that that's necessarily helpful. I just think it's kind of funny, and my brain has held on to it for so long that I figure it will spread the brain worms with everyone else. Now, finally, Lewis structures, how to draw them for molecular compounds. We've got a couple of steps for drawing Lewis structures for molecular compounds. Our first step, the first thing we've got to do is we need the correct skeletal structure for the molecule. We've got a couple of guiding principles here. Hydrogen atoms are always terminal. Terminal meaning they're on the ends. They're always terminal because they only have one bond. So we can't use them to connect two other atoms. We can't put them between two other atoms because they can only form one bond. So they have to go on the outside. We also will tend to put more electronegative atoms in terminal positions. So fluorine, for example, usually terminal compared to oxygen. Fluorine's got the highest electronegativity value. It likes to have extra electrons on it all to itself. It's going to have fewer bonds and more lone pairs. It's also going to tend to be on the outside. Symmetry is also tends to be stable. We'll learn other tools for coming up with good Lewis structures. But generally, if you can make it so that the left side and the right side, they're like mirror opposites, and the top and the bottom are mirror opposites, that's symmetry, and that's going to tend to be more stable. So that's our first step, laying out all of the atoms that we're using in our molecular compound. Our second step is we want to calculate the total number of electrons. So we want to sum the valence electrons. So I'd recommend writing out what are all of the elements that we have, how many of them do you have, multiply those by how many electrons they have, add all of those up. We can also have ions. So a negative charge means extra electrons, one for every charge. If you have a positive charge, that means take away electrons. And then we're going to distribute the electrons among the atoms. The way that I do this is I start with single bonds to connect, because all the atoms have to be connected. So we'll get the minimum number of bonds that we can. And then add lone pairs from outside in. So all of our hydrogens are going to get one bond. Anything that's not a hydrogen, things like fluorine, chlorine, bromine, oxygen, sulfur, those can have more than one bond. We'll add those bonds in so that everything's all connected. Add in our lone pairs to things like fluorine, chlorine, oxygen, sulfur, if they're on the outside. And then at that point, once all of our electrons are placed, if any atoms lack an octet, and all electrons are placed, we can form double or triple bonds to give octets. And we do that by moving lone pairs from outside atoms in. So we'll take lone pairs from atoms that are on the outside, the periphery, the more terminal ones. We can move those in to make double or triple bonds as we need to get our full octets. We're going to go a little over time so that we can do an example while this is fresh in our brains, or maybe a couple examples. We want to write the Lewis structure for CO. We only have two things. It's hard to get this one wrong for the skeletal structure. So first step, skeletal structure. We need to get all the atoms on the board. Just put them not on top of each other and you've done it correctly. So C and O. And then we need to add up the valence electrons. How many valence electrons does carbon have? Carbon has 4. We've got one of them. So we're going to have 4 valence electrons from carbon. How many does oxygen have? Oxygen has 6 valence electrons because it's in group 6A. Add those up, and we've got 10 valence electrons. In order for this to be a molecule, in order for this to be a compound, we need at least one bond connecting them. So place in one bond just to get us started, just to get things connected. We'll adjust that as we need to later. How many electrons did we place so far? 2. One bond is 2 electrons, so we've placed 2. So minus 2. Be stands for bonding electrons, and it's the minimum number of bonding electrons. We're not going to go back and change that at any point. And then we've got 8 remaining electrons. We've got 2 places that we can place them. We'll just share them evenly. So we'll give each of these 4 valence electrons. 4 electrons to carbon, 4 electrons to oxygen. That leaves us with 0 electrons left. That means all of our electrons are on the board, everything's placed. Now we need to check for octets. For our octets, carbon and oxygen have the same setup. Carbon has 1 bond. 2 electrons from the bond plus 1, 2, 3, 4 electrons, 6 electrons. Is that good? No, not good, right? We want how many? We want 8. We've got 6, we want 8. We've placed all of our electrons. How can we get more electrons? Sharing. So we need to share some electrons. So let's move in 1 electron from each. Let's scooch this over. So this would turn into this. So now we've got a double bond. So we've got 4 electrons from the double bond. And we've also got 2 plus 1 more is 3 electrons. So they each have 7 electrons. That's still not 8. We can move in 1 more electron from each. Space that a little better. Okay. And now it looks like this. We've got 6 electrons from the triple bond plus 2 more electrons in the lone pair. 8 electrons, that's an octet. They both have octets. Good Lewis structure. One more example, we want the Lewis structure for H2CO. So we have to place our H's, our C, our O. One way that you could do it might be to do something like this. There's a problem with this that makes it not as good as it could be. The problem is that we don't have left-right symmetry. So if we draw a mirror plane down the middle, the left side doesn't look like the right side because we've got carbon on the left, oxygen on the right. If we move the oxygen up to be on top, like that, now we've got left-right symmetry. That's going to be better position-wise. Why would we do this instead of this way? Why would we choose the left one, the green one, versus the red one? We want to put more electronegative atoms in terminal positions. So comparing the electronegativity between carbon and oxygen, which one has the higher electronegativity? It's the oxygen. So since oxygen has a higher electronegativity value, we're putting oxygen outside and carbon is going to be in the middle. So that's why we're choosing green over red. And then for our electron count, we've got a carbon with 4 valence electrons. We've got an oxygen with 6 valence electrons. We've got hydrogen. We've got 2 of them, 1 valence electron each. We add that up, we've got 12 valence electrons. To get everything connected, our hydrogens each need 1 bond. Those will go to the carbon. And our oxygen can bond with our carbon as well. How many electrons have we placed by putting down those 3 bonds? 6. So minus 6 bonding electrons. We've got 6 remaining electrons. Where can we put those remaining electrons? We can work from the outside, inside. Our hydrogens already have their duets, so hydrogen's good. Oxygen has 2 electrons. It needs 8. We can add our 6 electrons to our oxygen. So our oxygen has a full octet. Are we good? Not quite. Why not? Carbon. Carbon just has 3 bonds. So carbon currently has 6 electrons, but we've placed all of our electrons. How can we get more electrons to our carbon? Double bond. So if we do a double bond, we move 2 electrons in. Those electrons still count for oxygen, but now they also count for carbon. So we've got 1, 2, 3, 4 total bonds, 2 singles and a double. So carbon is now also happy. Oxygen is still happy because it's got 2 bonds. That's 4 electrons plus another 2, 4. 4 plus 4, 8 electrons. Questions about coming up with any of those Lewis structures? Yeah. They would end up being bent slightly down if we were thinking about the actual configuration. Yeah. You could put them at any whatever angles you want just for coming up with the Lewis structures, and then once we learn more concepts in the next chapter, then we'll learn about like how to put them at the correct angles and all that fun stuff. Okay, we'll pick up on slide 36 next time.